All right, my friends, I was hoping that you would just fall back on if in doubt, expand it out. So like, for example, for part A, the sum as n goes from 0 to 6 of 5 times -2 to the nth power. When you plug 0 in, you would just get 5. When you plug 1 in, you would get -10. So you'd be adding -10, which is just subtracting 10. When you put 2 in, you'd just have what we had with the last term, but times another -2, so plus 20. And so pretty soon you realize, like, oh, okay, well, they're just multiplying by another -2 every time. And then just make sure, so let's see, this would be n equals 0, n equals 1, 2, 3, 4. That was n equals 5, and we're supposed to go up to n equals 6. And so we'd have another 320 on there. There you go. Now for adding this together, totally up to you how you want to go about it. I'm going to start with 320, and then I'm going to subtract off 200. So I'll have 120 left. I'm going to add this 80 here. So I'm back up to 200. I'm going to add the 20. So now I have 220. Take off the 10. So I have 210, and then I'll add the last 5. So I'd get 215. There you go. So, and I hope for something like that, you'll always pretty much keep it that simple. Today, we're going to learn a formula for how to evaluate a finite sum of a finite sum of a geometric series like we are doing here. Finite meaning you only had like a finite number of terms. Here we had 6 terms, or 7 terms, that is. So we had a finite number of terms, and then geometric meaning, the terms themselves are generated by multiplying by the same constant value every time. In this case, it was -2. So we're going to come up with a formula for that. But for a problem like this, I hope you wouldn't reach for a fancy formula. You'd just do something simple like this. But when would you need a formula? Well, typically when you have a lot of terms. So like if your upper bound wasn't 6, if it was like 67, if there were 67 terms, and I don't know about you, but I wouldn't have wanted to do this one by hand if you had a lot of terms like that. So, okay, or I wouldn't have wanted to do it term by term anyway. Okay, so for part B, let's play around with this one. So your lower bound is 2. So let's show that term. So you'd have 64 times 1/2 to the 2 times 2, or to the 4th. And then when n was 3, you'd have 64 times 1/2 to the 2 times 3, or to the 6th. When n is 4, 64 times 1/2 to the 2 times 4, or 8. And then when n was 5, which luckily that's when we're going to stop, we'd have 64 times 1/2 to the 10th. There we go. Oh, goody. Now we get to simplify it out. Oh, gross. Okay. Well, 64 isn't 64 just 2 to the 6th? Pretty sure it is. And so this first term, you have 2 to the 6th, basically divided by 2 to the 4th for that part. So I'm going to come back and cancel that out in a little bit. Again, 2 to the 6th. The next one, you'd have it over 2 to the 6th. I'm just turning everything into base 2 because otherwise the math seems kind of hard. Or the arithmetic, I should say. All right, so now let's cancel the 2's out. So for the first fraction, and you'd be left with 2 squared, or 4. For the second one, you're left with 1. The third one, you're left with 1/4. And the last one, you're left with 4 down there. So 1 over 2 to the 4th is 16. There we go. And then let's make the answer look super pretty. So 4 plus 1 is 5. And then let's change 1/4 right here to be 4/16. So our final answer would be 5 and 5/16. And for later in the lesson, it might be nice to have this as an improper fraction. So let's also show that. So let's see, 5 times 16, 50 plus 3, so 80. So this is the same as 85 over 16. There we go. So I'll just box both of those. And then we got 215 for the first one. So congratulations if you got both of those. And really it's just a matter of if in doubt, expand it out. But now let's talk about a formula that you could use in a situation like this. Now, before you use the formula, you would need to know exactly what to use it for, because you don't want to use it on the wrong thing. So it's going to be a formula for situations like this, where you have a finite number of terms. Like in part A, we had 7 terms, and for part B, we had 4 terms. And it has to be for a geometric series. So, and then in the next example, we're going to prove what it is. But for now, let's go ahead and just tell you what it is, and then we'll practice using it. Let me see oh yeah, actually we end up practice using it again on the warm-ups, just to kind of show you that you do get the same answer. So anyway, let's do this a little out of order, actually. Let's do the proof last. So let's change this to example 2. And then let's do example 1 here. Okay, so for example 1, calculate each nth partial sum using the formula that the nth partial sum of a geometric series, it can be found by taking your first term, multiplying it by 1 minus your common ratio to the nth power, and dividing it by 1 minus the common ratio. Okay, and I know I just gave that to you. It's not the kind of formula I know how to lead people into. It is the kind of formula I can show you the proof for, which we'll do an example too. But let's have you practice getting the exact same answers we got in the warm-up, but this time by using this formula instead of expanding the terms out, okay? So I'm going to put out and let you do what you're going to do with it. Hopefully you get the same answers we did in the warm-ups, and then we'll go through it together in the next video.